Hello everyone. In the previous video, we started discussion on the interview questions that are asked in Java concurrency topic. In this video, we will continue that discussion. So let's start with the next question. What is a deadlock and how do we prevent it? Let's read. Deadlock is when all threads are waiting on each other forever. Deadlock. That means all threads are waiting on each other forever. This is the definition. It is not broken automatically. It can happen when a thread is waiting for an object lock that is acquired by another thread, and that other thread is waiting for an object lock that is acquired by first thread. So that means there is a cycle. For example, there are two threads, T1 and T2. And as we had taken an example in the series distributed concurrency control, so I won't be illustrating this in much detail, but at a high level, thread T1 will require, let's say, two things: lock on object A and lock on object B. Similarly, T2 will need a lock on object B and a lock on object A. Let's say T1 acquired the lock on object A, T2 acquired the lock on object B. Now, T1 is waiting for a lock to be available on B, but since this lock is taken by T2, it cannot proceed. Similarly, consider the situation of thread 2. It needs a lock on object A, but this lock is acquired by T1. So you see the cycle T1 and T2. T1 is waiting on T2 to release the lock on object B. T2 is waiting on T1 to release the object lock on object A. And hence this is a cycle and this is called as deadlock. Both threads cannot proceed. So there is no work done in this case. To prevent it, we use the optimistic concurrency control, which we already discussed in the distributed concurrency control videos. If you have not watched that series, that link will be appearing now, or you can find that in the description. Let's come to the next question. Give an example of how inter-thread communication works. So whenever someone asks you about inter-thread communication, the most prominent example is the producer-consumer problem. Basically, there are two threads, T1 and T2. T1 is producing something and T2 is consuming those. And T1 and T2 have to coordinate. Let's say the size of the buffer, the queue in between is only 1. So the size is 1. So T1 can only produce if this queue is empty. And T2 can only consume if this queue has the item. This coordination has to be done between thread 1 and thread 2. Thread 1 is producer and thread 2 is consumer. So consumer should not consume until producer has produced, and producer should not produce until consumer has consumed. That's what we discussed here. So let's take the example. I created a simple class called shared resource. Shared resource is this queue. This can be Kafka, this can be any message queue, let's say, which can act as a buffer. Private int data. So this is the data. And I also defined has data boolean variable to basically communicate if the data is available or not. So initially it is false. That means the queue does not have any data. Then I defined two methods, produce and consume. So let's take a look at produce method. So in the produce, I pass a value that, hey, thread 1, just put this value in the queue. So if the queue has data, then there is no sense of producing it, no sense of writing this value in the queue. So it will wait. It won't produce. It will wait for the queue to become empty. Wait if data is already present. Once that is done, that means this condition becomes false. This condition becomes false when has data becomes false. So it will set the data value to value, and it will say that, okay, now queue again has the data. So has data is equals to 2. It will just communicate by printing, I have produced this value. This is the value which is assigned to data and data is being printed here. Then it will notify other thread who is waiting on this. So it will notify, basically it will notify the consumer. So this consume method starts. While does not have data. So while the queue is empty, it will wait because there is nothing to consume. Once this condition becomes false, that means queue has some data. This has been set here that now has the data. So this condition will become false. It will print that I have consumed this data. And then since it is consumed, it will simulate this scenario of consumption by setting has data is equals to false. And then it will notify. It will notify producer that, hey, the queue has become empty. I have consumed the data. Now start producing the next value. So this is the code for consumer. Now, how do we use these two threads? So I define a main method. I create a simple object of the class shared resource. Let's say it is the queue, message queue. Then I create two threads. One is producer, one is consumer. So producer and consumer. So producer is nothing, new thread, and then I write the logic. I write that 5 times from 1 to 5. 1, 2, 3, 4, 5. You have to produce this value. So it will call this produce method. And it will pass the value here. Similarly, thread consumer will consume. So it will use this method. And it will also do so 5 times. So 5 values are produced and 5 times it is consumed. And since we are using wait and notify, so they can throw interrupted exceptions. And hence we are using try catch block here. Interrupted exception we are catching. And just printing in case this exception is thrown. And then I start these two threads. So as expected, what will be the output? Producer will produce one, then it will wait for the consumer to consume. So consumer will consume one. Then again, producer will produce two, consumer will consume two. So this is the series that will be produced, and hence you see produced one, consumed one, produced two, consumed two, produced three, consumed three, and so on. The next question is that can we change name of main thread? So earlier in part 1 we discussed that there is always at least one thread, that is the main thread, running in any Java application. Can we change its name? The answer is yes. So there is a method called as setName, which can be used to change the name of any thread. So if I do thread.currentThread, and upon that I call this method setName, and then I provide, let's say, any name, let's say Gaurav's thread, then the name of the main thread will become Gaurav's thread. So there is a method, just remember the name setName, through which you can change the name of any thread in general. Now, can two threads have the same name? The answer is yes, because two threads cannot have the same ID in a Java application, but two threads can have the same name. What if I call thread1 dot set name, and then I set the name as A backslash, and do the same for thread 2 as well. So two threads will have the same name, just like in a class, two students can have the same name, but their roll number will be different. Now the next question is wait versus slip. So wait is it releases lock and must be called within synchronized block. It is always called on an object. So if you just write wait, that means this dot wait, because this is implicit. This is the current object reference. It releases the lock. So when you call wait, then that thread will release the lock and is always called within the synchronized block only. Slip, on the other hand, halts the lock and can be called from anywhere. It does not matter. It is not a restriction that it has to be called from synchronized block. You can just write thread1 dot slip anywhere, even in the main method you can write. So it is always called on thread, just like here I gave an example, t1 dot slip. Now the next question is interrupted versus interrupted method. IsInterrupted is a Boolean method that returns a Boolean value if the thread is interrupted or not. So it is an instance method, whereas interrupted is a static method. So since it is static, you will write like this, thread dot interrupted. Now interrupted clears the interrupted state of a thread. So when I call this thread.interrupted, it will give me the value that is it interrupted or not. For example, thread was interrupted. So it will give me true. But the second time I call thread.interrupted again, it will give me false because it resets, clears the interrupted state of a thread. So false is reset to false only. But if the thread was indeed interrupted, that means first time it returns true. But then again, if I call, it will be set to false. When to use volatile keyword? Now, volatile is a keyword in Java, and when should we use it? So, you know that there is a concept of cache in operating system. And this cache basically caches the objects or stores the object which are frequently accessed. What happens is there is a chance that if some data is in cache, it might be, I am saying might be stale. That means outdated. So there are two concepts, cache, which is of three types, L1, L2, L3 cache. And then there is a concept of RAM in operating system. RAM always has the fresh data, but cache can have the stale data. Now, we should use volatile when we want that any update to the variable is read by other thread with the freshest value. So when a variable is marked with volatile keyword, let's say I write volatile int a, then anyone reading a's value will always read from RAM. So all threads read its value from volatile memory. Volatile memory is nothing but RAM. Volatile means it is not persistent, and RAM is not persistent random access memory. As soon as the power goes off or the operating system crashes, all the data in RAM is gone. It is not persistent data. Rather than from the cache and leading to most recent, the freshest value, fresh value, instead of stale value, which is possible in cache. So if basically if you want that the data that is read is always the fresh, read from the RAM, not cache, then use volatile. But since it is not read from cache, then it is somewhat slower because you have to read from RAM, and reading from RAM is slower as compared to reading from cache. The next question is, what is starvation? How to prevent it? In general, when you think of starvation, it comes to a term where some people are not able to get food. They are not able to get the resources because some other people, rich people, affluent people, are affording those things. Due to that, poor people are not getting those things. So this is the concept of starvation in social science. Now, in the terminology of threads, the similar concept applies. So thread starvation occurs when lower priority threads, that means poor threads, for example, are unable to execute because higher priority threads keep running. Higher priority is rich or affluent people. They keep running and keep using the resources indefinitely. That means these poor people, these lower priority threads never get the chance or do not get enough resources to run. Never. Or keep consuming CPU cycles. This leads to unfair resource allocation. So basically, some higher priority threads, they keep some resources busy so that lower priority threads. We discussed the priority in the part 1. If you have not watched that, then go ahead and watch that. There we discussed that priority can range from 1 to 10, any integer value, and 10 is the maximum priority. By default, the priority is 5. If you do not set a thread's priority, then it is a normal priority. So a priority of a thread with priority 10 will always run before a thread with priority 1 in general. So some of the mitigation ideas is ensure that threads get access in first out order using new ReentrantLock true. You need to pass this boolean true here in the argument. Then it will become a fair lock. We will come to the concept of ReentrantLock in the next question. But for now, understand this concept that if you pass true in the argument, then it becomes a fair lock. So it will lead to threads access in first out order. Reduces lock contention and allows other thread to proceed. So let's say there are 10 lines of code and the only critical section is line 5 and 6. Then why do you lock the entire 10 lines? We discussed this in the part 1 that just put a lock around here, 5 and 6, the critical section. So reduce the lock contention, basically reduce the area which is under lock. and this will allow other threads to proceed. Avoid setting extreme thread priority differences. For example, you said one thread's priority as 1, another thread's priority as 10. Now, obviously, this 10 and 1 are much apart, and hence this 10 thread with priority 10 will obviously get more priority as compared to 1. And this can lead to high chances of starvation. Use the yield method to let other threads proceed. We discussed that there is a yield method in the thread lifecycle. It will move a thread from running to runnable. But there is still no guarantee that CPU won't pick up the existing thread which yielded. The next question is, what is ReentrantLock? Now, reentrant is a class in java.util.concurrent.logs package. So this is the package name that provides explicit locking for better synchronization control compared to synchronized blocks. In the part 1, we discussed that there are two concepts, synchronized method and synchronized block. In this video, we discussed that there is a reentrant lock concept as well, which in general is better than synchronized block because it will provide you a mechanism to lock as well as unlock. In the synchronized block, you would write synchronized, and then you in the block you will write the critical section. As soon as this block is done, the lock is automatically released. Reentrant lock allows you many things. Let us discuss this. Reentrant, that means a thread can reacquire the same lock multiple times, allowing the same thread to acquire the same lock multiple times without deadlocking itself. It is still an exclusive lock. If you don't know what an exclusive lock is, go and watch my distributed concurrency control video. You can find that in the description. Go ahead and watch that to know what is the difference between a shared lock and exclusive lock. If a thread calls lock again, it does not block if thread is same that already holds the lock. So if the thread is same that is already holding the lock, it won't block even if you call lock again. Internally, it keeps a hold count and an honor thread. So what is fair locking? We already discussed. You just pass a true as an argument to new reentrant lock constructed. It will ensure the first in first out ordering of threads. So first in first out is the queue mechanism. So it is a fairness. It will ensure the fairness. For example, so I used the package and imported lock class and the reentrant lock class. I created a simple counter class where I set the count variable as 0 and then I create a lock which is a new reentrant. Note that I do not pass a true value here. So that means by default it is unfair lock. Now I made this method increment which will increment. Since this count is a critical section, it can be operated by multiple threads simultaneously. That's why I first acquire the lock. Then I increment and then I unlock the lock. So here I acquired the lock and then here I release the lock so that this lock can be acquired by other threads. Now get count is just getting the count reading, so I do not need a locking here. I just return count. Now in the main class, in the main method, I write counter is equals to new counter. I created an object of this class. Then I created two threads, which we'll call the increment method. This is equivalent of writing this lambda expression, counter dot increment. Then I started the thread and I called join on those so that main won't exit without the completion of thread 1, thread 2. And then I call the get count. So T1 and T2 will start both incremented by 1. So plus 1 by thread 1 and plus 1 by thread 2. So the ideal count should be 2. And since log is there, then this will ensure that count is always 2. So I will get the output as 2. Now it is similar to synchronized block. How? I can just write here. In the part 1, we just discussed that I can write synchronized. And then I can write the same logic, that count plus plus. That's all. This is here, it is equivalent to lock, this thing. And once this block is executed, here it is similar to unlock, which is this part. So this is similar to synchronized. But what are the difference with synchronized? Why we should use reentrant lock over synchronized? So locking and unlocking is explicit. In the synchronized, we do not unlock explicitly as soon as the block completes.
the lock is released. Here you can lock as well as unlock. So we have to write it, whereas synchronized is implicit. Locks allow locking and unlocking in any scope. Basically, you can acquire the lock in one method and release it in another method. Can have timeout using tryLock milliseconds. So you pass the milliseconds that he thread 1 try to acquire the lock and wait for 500 milliseconds. For example, 5 seconds you try to acquire the lock. If within the 5 seconds you cannot acquire the lock, just return. So that no thread is blocked. Allows fairness using new reentrant lock true. This we already discussed. Preventing thread starvation. But then it is slower than first in first out queue is used to ensure first come first serve basis. We always use try finally. So even if exception occurs, finally block runs and lock is released. For example, in the above code you see, I acquired the lock. What if some exception occurs here in the try block? This program will return, but the lock is there, it is acquired, so no other thread can proceed. So since finally is always executed, except there is a power failure or JVM crash, finally is always executed, no matter the exception is thrown or not. In the finally, generally the resources are released. So here I unlock the lock basically. So the same point here, that we generally use the try finally block, so that even in case some exception is occurring, I unlock so that other threads can proceed.
Let us come to the next question, which is what is the problem with tryLock? So tryLock is a method that we discussed, but it does not honor fairness. And that is basically the problem with it. So even if the lock is fair, that means if I create a new reentrant lock by passing true in the constructor value, even then, if I try to acquire the lock using lock.tryLock, it does not honor fairness. So that means it does not honor the first in, first out behavior. Then is there a workaround? Yes, there is a workaround. So instead of basically directly doing lock.tryLock, I can do lock.tryLock, then I can pass a timeout value of 0. And then in the time unit, I can pass time unit dot seconds. So for 0 seconds is the effective argument I am passing in the tryLock method. And this will make it a fairness with tryLock. So this will make the tryLock as fair. Coming to the next question, what is condition class in Java? So condition, as the name suggests, is used to put some condition on when to release or when to acquire the lock. In the previous questions, we discussed that there are 3 methods in the Java's object class. And since object class is the parent or the superclass of every class in Java, that's why wait, notify, and notify all, these 3 methods are inherited by default in all the classes. So similar to wait, notify, and notify all, condition class provides 3 alternatives: await, signal, and signal all. So wait is replaced by await, notify is replaced by signal, and notify all is replaced by signal all. So that's the concept of condition class. Let's take an example. So I created a lock using new reentrant constructor. Then I created a condition object, condition met, and lock.new condition. I created a method, method1, where I first acquire the lock. Then I wait for the condition to meet. So I say condition met dot await. I wait on this condition to meet. So my thread will be suspended here basically. It will move in the waiting state. In the method 2, I do a similar thing where I try to acquire the lock. Then in the try block, I do some operations, let's say execute some line of code. At the last, I signal on this condition. As soon as I signal on this condition, this is like a notify. And since it is notify equivalent, it will notify this thread, which is waiting on condition met. And since I called this signal on the condition met variable itself, this will be freed. So it will move from the waiting state and can execute the rest of the lines. So it will resume here. Now, one thing you noted that I have enclosed the await and signal in the try finally block. Why is that so? So we will come to this, but first let us move ahead and read further. So, but there is a concept of spurious wake up. Spurious means fake or false. So thread can wake up in a false way as well. When a thread can wake up without a signal, so there is no signal, but thread has woken up. Hence, it is always recommended to use await in a loop. Here, if you note, we have used await without any if condition or in a for loop. So this is actually not the correct way. So I would say this is not the correct way. Why is that so? Because a thread can wake up without a signal. This is a concept of spurious wake up. Now, below we use while instead of if. So I created a method consume. I acquired the lock. Then in the try finally block, I wrote while loop count is equal 0. While the count is 0, added dot await is executed. So the first time thread comes here, it moves in the waiting state. Let's say some signal comes, some false signal comes, called as spurious wake up. So this thread will wake up. But since it is in a while loop, this condition will need to be executed before the exit of while loop. So it will see that count is still 0. That means it will again go in the waiting state. And that's why it is recommended to use await in a loop. So we can rewrite the producer consumer problem. We have seen previously how to write the producer consumer problem using wait and notify. Can we write it using the condition class as well? Let's see. So it is very simple. Create one lock, then create two conditions. One is for adding, one is for removing. So lock.new condition for added, lock.new condition for removed. Then we have two methods. One is the producer, one is the consumer. So for producer, it will try to have a lock because it is trying to add. But while the count is equal max count, that is the maximum capacity of message queue or buffer. Till then, it will await on removing. So while the remove operation is done, it will await. Once that is done, it will add the data and it will signal that I have added the data. And finally, it will unlock. So even if some exception is thrown, that's why we use the try finally. Even if some exception is thrown, we know that finally block is always executed. And hence, we always want to ensure that any resource which we have taken should always be released or freed up. And that's why we always unlock or clean up the resources in the finally block. It is executed no matter if the exception is thrown or not. In the consume method, it again tries to get the lock. And while the count is 0, that means message queue is empty. It will wait for adding. Once add is done, it will exit the while loop and it will get the data. Then it will say that I have got the data. Then it will signal the remove that I have removed it. So once removed signal is done, this thread will be woken up. And when the added signal is done, this consumer thread will be woken up. So that's the concept of writing producer consumer problem with condition class. Let's move ahead. So question number 25 is writing the code, which I will cover in part 3, where I will do a live coding and we will see a couple of problems on lead code. Similarly, question 26 is also a coding exercise. So I will take this up in the part 3. Let's move ahead. What data structures are synchronized in Java? So Java provides out-of-the-box data structures under collections. So you might have heard of list, you might have used hash map and hash set. These are the most frequently used collections. These are actually data structures which you don't have to write and are provided out of the box in Java. So out of these data structures, do you know what all data structures are synchronized? We know the concept of synchronized method, synchronized block, then ReentrantLock. Can you tell what data structures are synchronized by default? The answer to that is, first is some of the legacy collections like stack and hash table are synchronized. But they are very slow because a global lock is there. Nowadays, stack is considered a legacy collection. So the recommendation is to use ArrayDQ to simulate stack problems and use concurrent hash map instead of hash table. The second is any collection of this type, collections dot synchronized x, where x can be replaced by something. For example, it is replaced by list. So collections dot synchronized list is also a synchronized collection in Java. Third is multi-threading like copy on write array list and concurrent hash map. Fourth is for atomic operations where we need transaction nature, either all or none behavior. We use java.util.concurrent.atomic package like atomic integer array. So this is the package name and this is a sample class. So these are the four examples, but the most prominent ones are stack is synchronized, array dequeue is synchronized, concurrent hash map is synchronized. Copy on write array list is synchronized. These four collections are, I think, more than enough. If you tell these names, then you have successfully answered what data structures are synchronized in Java. Now the next question is, which data structure should we use when? The first scenario is it is single threaded. Second scenario is it is multi-threaded, but it is a read heavy system. The third scenario is it is multi-threaded, but it is a write heavy system. The first scenario is very simple. If there is only a single thread, then there is no concept of critical section because no other thread is there, which can cause inconsistency writing. So we can use non-synchronized collections like array list, hash map, etc. But if it is multi-threaded and read heavy, that means since the read part is heavy, we read more often than we write, then we need a good read performance. And hence we use copy on write array list and copy on write array set. But if it is multi-threaded but write heavy, that means we need a better write performance as compared to read, because the extension of writes, the number of writes is more than the number of reads. So then we will use concurrent hash map or concurrent linked queue. So a read heavy system will be, for example, YouTube. On YouTube, let's say 20 YouTubers upload, but 80 YouTubers watch. So that means there are more reads. One video is uploaded, but it is watched by 100 viewers. So it is the ratio 1:100. So for example, let's say some IoT device is pushing the sensor information or the sensor data or the logs are generated. So this is the example where writes are much larger than the number of reads. In that case, we use these data structures. Coming to the next question, what is compare and swap? So compare and swap or compare and set is a concept which is taken from low-level programming as well. So let's read. Java provides atomic data structures in the java.util.concurrent.atomic package. This we already discussed here. So this is not a new thing to us. These use low-level CPU instructions, compare and swap, CAS. So compare and set or compare and swap to ensure atomicity without traditional locking. For example, include atomic integer, etc. So atomic integer is a class which is a prominent example of compare and set. Its internal working is based on CAS. So let's read what a CAS is. So CAS is an atomic operation. So either all or none. Used in multi-threaded programming to update a variable only if it has not been changed by another thread. What does this mean? So we know that CAS means compare and set, yeah, or swap. So first you compare that whatever value you read is the same as the variable's value now. And if it is same, then only use set or swap. So how does this prevent locking? So we need locking because let's say two threads are there, thread 1 and thread 2. And there is a variable, let's say a, it has a value 1. At time t1, both threads read that a has value 1. Context switch happened, so t2 also get a chance and read that a's value is 1. Now context switch happened to 1, t1. Now it incremented the value and committed. So now a is 2. Now thread 2 is under the impression that the value of a is 1 because it has read the data which is now stale. So it will operate on this data only. And it will proceed to the next line and it will also increment to 2 and will write it to database. So A's value is now 2. Is it good or is it consistent? The answer is no. Why? Because T1 incremented, so A's value should be 2. Then T2 incremented, so A's value should be 3. So 1 to 2 and then 2 to 3. 2 is done by T1 and 3 is done by T2. But due to this old data, stale data, T2 is doing a wrong increment. But what if before incrementing this, it would have read if my value, which is 1, which is read by me, is the same as the current value of A. So it has read 1, but the current value of A is 2. So it will say that 2 is not equal to 1. So it will abort the operation and will restart here. And this is the concept of compare and set. Instead of putting a lock, it first compares if the value that has been read is the same as the variable's value now. So it is a low-level CPU instruction that avoids the need for locking. How? We just discussed in this example. Like synchronized blocks and making operations faster and more scalable. Let's take an example. So from the package, I imported the atomic integer class. I created a test class, CAS test, where I created a count variable of type atomic integer with initial value as 0. So count's value is 0 now. So I will write count is equals to 0. But this is not a simple variable. It is of type atomic integer, which uses CAS internally. In the main method, I write count dot compare and set. So it will compare and set. So first what it will compare with 0. So value of count is 0 and it is comparing with 0. So 0 is equal 0. That's true. So it will set to 1. So now count's value is 1. Then it prints. So since it is able to update, it will print update success true. So update success true and current value is 1 now. So it will say current value is 1. Now next it will again do compare and set. So compare with 0. Now count's value is 1 actually. So 1 is not equal to 0. So I will say 1 is not equal to 0. And this is a false condition because 1 is not equal to 0. So it won't set it to 2. So it will write update success is false and current value is still 1 because the value was not updated. So this is the example of compare and set. So what are the advantages? The advantages of using compare and set is that first thing is it is non-blocking because we are not using any locks. So no thread locking, that means better performance. We are using low-level CPU instructions. Second, it is fast and efficient. Uses CPU instructions instead of JVM locks. CPU works on low-level mechanism, and hence the reason that this is fast and efficient. Consider this, why we say that C language is faster than Java. Because C is a low-level programming language when we compare it to Java. Java has a lot of abstractions built on top of existing structures, and hence C is faster. So similarly, CAS is much faster than a program written in lock mechanism. Third reason is avoids deadlock. Since there is no lock, there is no possibility of deadlock, since no thread is ever waiting for a lock. But there are some disadvantages. There is no thing as a free lunch. So disadvantage is spin loops. So if multiple threads keep failing CAS, they keep retrying, wasting CPU cycles. So let's say here I put this in a loop. So it will keep comparing it with 0. But since the value of count is now 1, it will never be 0. Hence, this loop will keep executing. So this will waste the CPU cycles. Then another problem is ABA problem. ABA problem is, let's say the initial value was A, it was changed to B, and then again to A. Can you tell if this A and this A is different? The answer is no. So if a value changes from A to B and then B to A, compare and set cannot detect it. It just matters what is the value when it is reading. So reading time it is A, initial reading time it is A. So it does not matter if in the intermediate state the value was changed. So CAS cannot detect it. The solution for that is use some other class. For example, atomic stamped reference. Above we use atomic integer. But then the recommendation is if you want intermediate results also to be considered, then use atomic stamped reference class. Coming to the next question, what is the difference between mutex, lock, and semaphore? This I will create a dedicated video because there is a lot of confusion between mutex and semaphore. Some say that is semaphore same as mutex or mutex same as semaphore with permit count as 1? The answer is no. So mutex in no way is equal to semaphore. And I will create a dedicated video on this soon. But in the scope of this video, let's discuss. So all three are synchronization mechanism: mutex, mutual exclusion, lock, and semaphore. Let's come to the first thing, mutex. Mutex stands for mutual exclusion. So mutual mute exclusion means EX. So synchronized in Java acts like mutex, where mutex is owned by the thread that locks it and must be released by the same thread. That's correct. Only one thread can enter when we write synchronized in a contract of method. So that acts like a mutual exclusion. If another thread tries to acquire the mutex while it is locked, it is blocked. So this we already discussed. Second thing is lock. Reentrant lock in Java acts like a lock. Can support tryLock, we discussed already. Non-blocking attempt to acquire the lock with timeout. We can pass the milliseconds timeout and then it will respect the timeout. It can be fair. We already saw how to make tryLock as fair or how to make a reentrant lock as fair. Fair means assign locks in a FIFO manner, first in, first out manner. The third thing is Semaphore, which is another synchronization mechanism. Semaphore class in Java acts like a semaphore. So Semaphore allows multiple threads to access a resource simultaneously. Now here the confusion comes. Some say that mutex allows one thread. So if Semaphore, we say that multiple threads, I set the count as 1. So Semaphore is also equal to mutex. But there is some subtlety which we will discuss in a separate video, in an upcoming video. So if you have not subscribed till now and you are watching till now, it will be a great addition to your skill if you subscribe. When I post the video, you will get a notification and you can watch immediately. Otherwise, what will happen is this next video will be skipped and you won't get any notification. So Semaphore has a permit count. I will write as PC, determining how many threads can hold it at once. So if I set as permit count as 2, that means in the critical section, 2 threads can enter at a time. Each thread when entering reduces the permit count by 1. So when T1 enters, permit count will be reduced to 1. That means one other thread can enter. When T2 enters, it will reduce to 0. As soon as it is 0, that means no other thread can enter. So from the java.util.concurrent package, I import the Semaphore class. I create a shared resource class where I create a Semaphore variable with permit count as 2. So as we discussed here, 2 threads can enter at a given moment. 2 is the maximum. It is not necessary that 2 threads need to enter. Maximum 2 threads can enter. Then I define a method, access. So in the try block, I do semaphore.acquire. So as soon as it is acquired, the permit count was 2, it is reduced to 1 because this has acquired the lock. I say that thread.currentThread.getName and then is accessing. This will be printed. Most probably it can be main. Then I do some mock, basically for 1 second, it is sleeping to simulate some working execution of some code. Once that is done, if no exception is thrown, we will go to the finally block. So finally, in the finally semaphore.release. So as soon as it is released, PC was 1. It will again restore to 2. So this lock is released, release the permit. If some exception occurs, let's say interrupted exception was thrown, it will print the stack trace. But since finally is always executed, no matter exception is thrown or not, that means we will always restore the permit count. So that's why we release always in the finally block. So we do not need to worry about if exception is thrown, then we need to take this route, or if the exception is not thrown, then we need to take this route. The last question in this video will be future versus completable future. We already discussed that when we do executor service.submit, then a future variable is returned, future value is returned. So as we discussed earlier in part 1, future is used as a reference to the result of an asynchronous operation. But there must be some limitation with future class, and that's why completable future was introduced in Java 8 to overcome the limitations of future class. So what were the limitations? First thing to understand is that what are the limitations of future class. If we can understand the limitations, then we will be able to appreciate why completable future was introduced. So first limitation is that the get method future.get is a blocking method. This we already discussed. So unless the method execution completes, main thread won't execute further. So if server takes too long to process, whole code will keep waiting, no timeout. Second limitation is we could not attach a callback method once the result is available. So we cannot do the chaining of operations. So chaining of operations is not possible. For example, I can do x dot y. Once this is done, then I do z dot, then a dot, something like that, like we do in the Java streams. So we cannot do that. Third limitation is we cannot run multiple futures parallelly. And fourth limitation is there is no exception handling in future class. So to overcome these 4 limitations, get method is blocking, we cannot attach a callback method, we cannot run multiple futures parallelly, and there is no exception handling in future class, the completable future was introduced in the java.util.concurrent package. So let's take an example. I created a simple demo class, completable future demo. In the main method, I wrote that completable future dot supply asynchronous supply async, and then this lambda expression will return Gaurav. Once I do completable future dot get, this will be executed and it will return Gaurav. So it will print first Gaurav and then main. So this is the first example of completable future. Let's take the second example. Again, in the demo classes main method, I wrote task1 is equals to completable future dot supply asynchronous Gaurav and completable future dot supply asynchronous Kabra. So task1 should be concerned with Gaurav and task2 should be concerned with Kabra, because these lambda expressions are returning Gaurav and Kabra respectively. Then I basically started the execution of both the tasks simultaneously. So I wrote completable future dot all of task1 and task2. Once these tasks are scheduled, I do task.get. So now it is written as get to be compatible with future, because there we used to write future.get. But here you can write task.join as well. So that's also fine. So you can write tasks.join. That's also absolutely fine. So it will just wait for all tasks to complete, does not return results. It will wait for all tasks because I wrote all of. Once the execution is done, the control will come on this line. So it will print task1.get as usual, it will print Gaurav. Task2.get, it will print Kabra. And then main will be printed. So this is the second example where we are executing multiple futures together. Now, third, executing multiple completable futures together, because these are completable futures, not futures. Now coming to the third example, let's see. In the main method, I created one task, completable future dot supply async, then Gaurav. Dot then apply string colon colon to uppercase. So this can be written as dot then apply whatever value is written str do str dot to uppercase. This is equivalent of writing that. So you see, I am doing a chaining of operation. If this is X, if this is Y, then I am doing Y. And if it is Z, then I am doing dot Z. So this is the chaining of operations. Once this operation is done, then this operation is picked up. So when I do task.get, this will be returning Gaurav, but then it will be converted to uppercase. So it will print capitalized Gaurav. And then main will be printed. So this is the example of chaining the operation. Let's take the fourth example. In the main method, I created a simple task, again, completable future dot supply async. Then here I want to demonstrate the exception handling, which is introduced in completable future, but is not present in the future. So I deliberately write 0 by 0, which is mathematically undefined. So since it is undefined, I wrote a dot exceptionally E, then I written -1. So here we can write another logic, but here I just wrote -1. So you can write, when I write system.out.println task.get. So this will be executed. 0 by 0 will throw an exception. And then this exception will be caught and will return -1. So this will print -1. And then main. So main is printed. So that's all for this video. Stay tuned for the upcoming videos by subscribing to the channel. If you found these questions useful and you are liking the series, please consider sharing and subscribing to the channel. If you have any topic in mind which you are finding hard to understand, then please feel free to comment and I will pick up that topic as part of one of the future videos. Thank you so much.